January 15th. 5 days after the strike at Engels Air Base, Moscow believed the situation was under control. 2 damaged Tu-160 bombers were rushed into emergency repair. They were quickly pulled out of public view. But that decision triggered something far worse. When a strategic bomber enters overhaul, it consumes engines, test benches, and critical certification capacity. That night, the follow-up strike did not just destroy another aircraft. It transformed a battlefield loss into an estimated $3.4 billion industrial disaster. 3:40 a.m. Inside the Kazan Gorbanov aviation plant, the lights were still on. This was not because of urgency, but because the production schedule had already collapsed. Russia had made a decision months earlier that would quietly seal its own vulnerability. Instead of dispersing damaged Tu-160 bombers across multiple airfields, Moscow concentrated them at Kazan for deep overhaul. On paper, it looked efficient. In reality, it was dangerous. Each Tu-160 requires an average of 16 to 20 months of restoration. This process involves more than 41,000 individual components. Nearly 70% of those parts rely on high-temperature titanium alloys.
On section 7.
These materials cannot be substituted or rapidly reproduced. The plant was never designed for this volume of work.
Doesn't align with the structural
its operational load had climbed to 134% of rated capacity. This pushed both machinery and personnel far beyond safe margins. The real bottleneck was not space, but certification. Only 48 engineers across the entire Russian Federation are authorized to approve NK-32 engine reassembly. During night shifts, that number drops to fewer than 9 specialists on site. If even one inspection cycle fails, an entire engine module is frozen indefinitely. This was no longer just a factory. It was a single pressure point holding together Russia's strategic aviation fleet. And pressure points do not need to be destroyed. They only need to be stressed until the system breaks itself. As dawn approached over Kazan, Russia believed its bombers were finally being protected. In reality, they had been gathered into the most fragile configuration possible. While Russian commanders focused on airframes and flight readiness, Ukraine was studying something far more dangerous. They were not looking at where the bombers were parked, but what allowed them to exist at all. Destroying a Tu-160 creates a spectacle, but crippling the system behind it creates a terminal silence. Ukrainian analysts began tracing the bomber fleet backwards, step by step. They examined maintenance logs, overhaul cycles, and industrial dependencies. The conclusion was immediate and unsettling. Every Tu-160 eventually depends on a single component, the NK-32 engine. Without it, the aircraft cannot fly, cannot deploy, and cannot even be certified for storage. Each NK-32 requires more than 6,300 hours of precision machining. Inspection stages are measured in microns, not millimeters. Across Russia, fewer than 50 engineers are legally authorized to approve engine restoration. Fewer than 18 can certify turbine cores exposed to extreme thermal stress. During night shifts, that number drops into single digits. That is not resilience. That is suffocation. The tension in Kyiv intensified with the next discovery. Nearly 3/4 of Russia's reserve NK-32 modules were concentrated inside one industrial corridor. They were within walking distance of the test stands themselves. A single disruption there would not just ground one bomber, it would pause the entire fleet. This realization triggered a strategic fury.
The pressure readings spiked
For years, Russia projected strength through size and intimidation. Yet its most powerful weapon now depended on aging specialists and paperwork that could not be rushed. Next, we move to the wall Russia trusted, and why it was never as solid as it looked. 110 and out. Above Kazan, the air defense network was fully awake. From the outside, the city appeared wrapped in steel. S-400 systems dominated the outer ring. Their radars swept hundreds of kilometers beyond the horizon. They tracked aircraft long before pilots knew they had been detected. Beneath them, Book M3 batteries waited in constant rotation. These are optimized to intercept targets flying too low for strategic radar. Closer still, the final barrier stood ready. Panzer S1 and Tor M2 units guarded the industrial zone. These units are capable of firing within 5 seconds of detection. Overlapping everything was the Krasuka 4 system. It flooded the air with electromagnetic noise, strong enough to disrupt navigation across entire districts. The numbers inspired confidence. A single S-400 battalion can track over 250 targets simultaneously. Each interceptor carries enough kinetic energy to obliterate reinforced structures. At peak readiness, the system consumes more power per hour than a city of 80,000 residents. Russian commanders were certain of one thing: no unmanned aircraft could survive long inside this zone, 90 seconds at most. That was the estimate written into their defensive doctrine. Yet doctrine depends on expectation. The expectation was that the enemy would come from the sky. As operators stared at glowing radar scopes, the battlefield was already shifting. It moved toward the space their systems were never designed to dominate. 2:05 a.m. The first contacts appeared exactly where Russian radar crews expected them. They were at high altitude, with clean trajectories and large radar signatures. To the operators, the picture looked familiar. It was the classic profile of cruise missiles entering engagement range.
I'm showing an unauthorized
there was
contact
no
bearing
hesitation.
049er.
The Nebo M radar
Designate
prioritized
secondary
the
track,
targets
full
and
course.
fed data to the S-400 fire control network. Within seconds, tracking locks formed across multiple screens. For the Russian military, this was the moment the system was built for. Interceptors launched in rapid sequence. Each missile cost more than $2 million and required hours of recalibration after launch.
Speed high.
They consumed a finite stock that could not be replaced quickly, yet doctrine demanded immediate action. The targets were glowing on the screens like beacons. What the crews did not know was that these objects were not weapons. They were radar profile decoys. They were engineered to imitate the speed and signature of Storm Shadow missiles with 90% accuracy. They were just realistic enough to trigger full engagement protocols. In less than 4 minutes, the system achieved what looked like total success. Targets disappeared, and confidence surged. But that victory came at a hidden cost. While million-dollar interceptors exploded in the upper atmosphere, the S-400 had done exactly what Ukraine needed. It had exhausted attention, ammunition, and time. With the sky declared secure, every sensor was now looking in the wrong direction. 218M movement appeared near the ground, where long-range radar struggles most. New contacts slid along riverbanks and terrain folds. This was the engagement zone of the Buk M3. The system reacted without delay. Within 8 seconds,
Status report, Mark.
tracking radars
Are we
locked
stable?
and launch vehicles
All green,
rotated.
Commander. We held it together.
Interceptors surged forward, guided by real-time updates. Each missile carried a fragmentation charge designed for low-flying targets. Initial results favored Russia, and several drones vanished from the screens. Operators believed the breakthrough had been contained, but the pattern quickly changed. The remaining targets refused predictable flight paths. They climbed briefly, then dropped sharply between radar pulses. Terrain masking further distorted the tracking data. Every maneuver forced the Buk system to recalculate its intercept geometry. That recalculation cost precious seconds. Missile usage climbed rapidly. Batteries fired beyond their recommended tempo to maintain coverage. Engagement rates surged at 3 times the doctrinal limits. Launch tubes were drained faster than the crews expected. The Buk M3 continued scoring hits, but control was slipping. Each delay shortened the reaction distance. The system was still fighting, but it was no longer shaping the battlefield. As the drones closed in, the pressure fell toward the final defensive ring. 2:27 a.m. Responsibility shifted to the final line of defense. Panzer S1 and Tor M2 units activated almost simultaneously. Their sensors snapped toward multiple vectors at once. At this distance, reaction time was measured in seconds. The dual cannons of the Panzer erupted first. They released thousands of rounds per minute into the darkness. Interceptors followed, but the targets were now too fast and too numerous. On paper, the system was lethal. In reality, it was being forced to do too much at once. Each Panzer vehicle can prioritize only 4 targets per second. When incoming tracks exceed that limit, the system cues the engagements. Queuing creates delay, and delay creates overlap. The drones exploited this immediately. They split into small clusters, approaching from offset angles and uneven altitudes.
I need clearance on the
Radar
bypass
screens
valve
flooded
now.
with competing
Acknowledged.
signals. Operators were forced to
overriding
choose
the
which
system.
threat to kill and which to ignore. The Tu-160 attempted to compensate, firing repeatedly to cover the gaps. Within moments, the defense turned into a state of strain. The systems did not fail, but they were overloaded. Overload is invisible until it is irreversible. As the guns continued firing, a narrow window opened for the next phase. 2:33 a.m., Russian commanders deployed their final safeguard. The Krasuka 4 surged to full output, saturating the air with electronic noise. Within seconds, GPS signals and satellite links vanished. Standard drones would have lost orientation and crashed. Inside the command center, confidence briefly returned. Jamming had always been the reset button, but this time, nothing fell. The remaining drones did not slow down or scatter. They continued forward with unsettling precision. The Krasuka 4 was disrupting transmissions, but there were no transmissions left to disrupt. The drones had switched to autonomous navigation. They were relying on laser-based inertial systems and onboard optical sensors. Instead of listening, they were observing. They compared terrain shapes and building outlines against preloaded maps. Their positional error remained under 2 meters. The electronic storm achieved nothing. There were no guidance channels to sever and no operators to silence. For the first time that night, Russian defenses faced a threat they could not interfere with. The battlefield went quiet because the drones no longer needed permission to continue. 2:41 a.m. The final drones dropped beneath the factory lights. They flew so low that radar no longer mattered. At this range, interception was irrelevant. The outcome depended on physics alone. They ignored the wings and fuel lines of the bombers. Their target was the NK-32 engine. Each drone aligned with the intake path, diving into the narrow channel of the turbine core. Impact occurred instantly. The warheads released thermal energy exceeding 4,600 degrees Celsius. This is far beyond the tolerance of aerospace-grade titanium. Under that stress, the metal collapses. Compressor blades lost their shape, and turbine discs warped. Internal balance vanished before suppression systems could react.
This measurement doesn't
Fire
align with
spread
structural
inside the
supports
maintenance
here.
bay as specialized
We are already
lubricants
behind
ignited.
schedule.
Nearby engine
We can't
modules
afford a
overheated
rework.
past the point of recovery. What began as a strike expanded into a cascading failure. Within minutes, the engines were eliminated. For Russia, this was not just the loss of a single bomber. It was the loss of operational continuity. A Tu-160 without a certified NK-32 cannot be returned to service. As smoke filled the hangar, the damage spread far beyond the factory walls. What Russia lost was time. The one resource no military can stockpile. The destruction of these components triggered a freeze across the maintenance network. Inspections were suspended and documentation halted. Engines awaiting approval were locked in place indefinitely. Even intact aircraft became grounded assets. The ripple effect was severe. Every additional flight hour now carries increased risk for the remaining fleet. Engineers estimate that extended operations accelerate engine fatigue at an unsustainable rate. Dispersing the bombers created another dilemma. Moving them thousands of kilometers reduced readiness and increased logistical strain. The real shock, however, came from the loss of capability. With test benches disabled, highly specialized technicians were left idle. Skills that require constant repetition began to atrophy within weeks. This was a structural fracture. Russia can still possess and display its bombers, but sustaining a strategic force requires continuity. And that continuity has been severed. The attack disrupted the rhythm of an entire system. In modern warfare, systems fail long before armies do. This operation was never about producing dramatic footage for headlines. It was designed to expose a deeper truth. Power today is measured by the resilience of systems. Russia lost leverage because the structure supporting its aviation fractured. When maintenance stops and certification fails, advanced weapons become symbols rather than tools. Ukraine did not confront power directly. It attacked dependence. It targeted the rhythm that keeps the machines alive. If low-cost systems can disrupt assets worth hundreds of millions, the nature of dominance changes. It is no longer about who owns more weapons, but who understands where they break. Is this the future of warfare, or just the opening chapter of something more dangerous?
The pressure readings spike.
Share
right
your
before
thoughts in the comments. Subscribe so you don't miss our next breakdown of how modern wars are decided.